Windows, boo. Linux, boo. macOS, I shouldn't even have to mention it, but boo. I'm so tired of operating systems holding me back, man. I'm just a real gamer trying to push my hardware to the limits. Wordle isn't gonna solve itself. It's ridiculous. Do you know how many million little things your OS is doing every single second? This is my hardware. I should be able to talk to it without Bill Gates personally listening in on all my conversations. But what about Linux? Wrong answer, buddy. I don't work for Amazon. I don't want to deal with managing thousands of packages. I just want to get closer to that delicious bare metal. I want to feel the silicon run through my fingers as I take full control of the system. Just my hardware running a classic arcade game the way it was meant to be played, written in assembly without an operating system. This is total freedom from big tech. Reject OS. Return to metal. This is the BIOS, the basic input-output system. This is firmware, as in sandwiched between the hardware and software, that provides services and low-level control of the physical hardware through an abstraction layer, so programmers and operating systems don't have to worry about exactly which chips are present in the underlying machine. As long as the BIOS provides the same functionality, they couldn't care less what was running the code underneath it. Except that this isn't a BIOS. This is the UEFI, Unified Extensible Firmware Interface. To use the correct terminology here, this computer is currently running a UEFI application to provide the user with an interface for firmware settings. UEFI itself, originally EFI, and you can still call it that, was an invention of Intel from the late 90s, early 2000s, made to provide additional services that the traditional IBM PC-compatible BIOS wasn't able to. Intel's implementation of UEFI was later made open source and is now maintained by the volunteers of the Tiano Core community, who've also created development tools such as the EFI Development Kit 2, targeted at the C language, so much too rich for my blood. The basic UEFI implementation provides two different kinds of services: boot services for things like memory management, loading, and then running other UEFI applications, and runtime services like checking the date and time or resetting the system. There are dozens of other additional UEFI protocols as well, and I'll explain those as they become relevant. On power on or reset, your x86 64 CPU will, in real mode, jump to the reset vector at memory address FFFFFFO, which will contain the address to the initialization instructions, where the CPU will enter protected mode, verify the firmware, initialize the memory, load the UEFI drivers for input, storage, and graphics, then load the UEFI boot manager, which will check the boot order list and load the associated EFI application. This could be the firmware settings application, the Windows boot manager, Grub, or any other EFI application, like mine. This is where mine will go. Starting with a blank file, writing a UEFI program is not all that different from writing a normal program. I'll create two sections, the .data and .code section, and I'll call the entry point EFI main. With the return instruction, this is a fully legitimate program, but I'm not trying to create the smallest EFI program. I want it to actually do something. As it happens, UEFI provides abstractions for console input and output in a similar way to Windows, but I'll have to grab it manually. If this were a C program, it'd be easy to see that the EFI main procedure has been passed in two parameters: the image handle of the current EFI application and a pointer to the UEFI system table, which itself contains a list of pointers including one to the boot services table and one to the runtime services table, plus pointers to the simple text input and simple text output protocols. The text output protocol structure is mostly a list of pointers to various functions, the most important right now being the output string procedure. Back in the assembly program, the two parameters are passed in through the RCX and RDX registers, so I'll save those for later reference. And then I'll also create a variable to store the text output protocol. Since I'll be running this program on a 64-bit processor, the UEFI application must be 64-bit as well, so all the pointers in the EFI tables will be 8 bytes. The output protocol is the 7th entry. With the other sizes of the previous entries being what they are, the pointer to this protocol is located at the 64th byte in the table. That's fairly easy to grab onto, and I'll store that 8-byte pointer in conout. Then use this pointer to grab the procedure I'm interested in, output string, which is located at the address of conout plus 8 bytes. To use this procedure, it takes two parameters, again passed in through RCX and RDX. First, a pointer to the simple output text protocol, then a pointer to a string of 16-bit Unicode characters. Luckily for basic Latin, it's just the same as ASCII but double width. Then time to call that procedure, which will jump to that address, execute the code, and output our string onto the console. The program in this state would run just fine, but after continuing to the return instruction, it'd either go into the next boot option or maybe just open up the firmware settings. Either way, I want to pause execution here before going on. So just like with con out, I can save the pointer of the simple text input protocol, and then using that pointer, grab the wait key event, which isn't a procedure, it's an EFI event. That just means that to wait for the next key, I need to use the wait for event procedure from the boot services table, so I'll grab that pointer as well. Then I'll pass in 1 to say that I'm only giving one event handle, the wait key event, the pointer to where I want the return data to go, and then call the wait event procedure. And this should wait for a single key press before moving on. This assembly code is now ready to get assembled, and interestingly, UEFI executable images are packaged as PE-COF images, as in the same as Windows images, which means that I can use the 64-bit Microsoft macro assembler to create a regular object file, then use the Microsoft Visual C++ linker with the subsystem set to EFI application and entry to EFI main to get a .EFI program, ready to be loaded and run by the PC's UEFI firmware. So, does it run? Yes, it works. I'm free from the shackles of the operating system. At least I will be once I actually run it without emulation. As it happens, UEFI applications are much easier to test on actual hardware than through emulating a PC in software. I did eventually figure out how to get QEMU to load and run this program for testing purposes, but it still required external hardware. My UEFI program is sitting outside my computer on this flash drive. This drive specifically uses a GUID partition table, not a master boot record, and has a dedicated EFI system partition containing the file structure EFI/boot, in which is placed the EFI application named bootx64.efi. That's just where and how the computer expects to find the UEFI application. To test this on hardware, I'll need a PC, and luckily, Geekom has just sent me their Geekom A9 Max for this very purpose. This machine has an AMD Ryzen AI9 HX370 CPU. I figured it was better to go with AMD this time since they're the ones who invented the x64 standard. It's a sleek little computer, and I know what you're thinking. Only 4 USB 3 ports, 2 USB-C ports, 2 Ethernet ports, 2 HDMI ports, and a front panel headphone jack? That's not nearly tripophobic enough for me. Well, you're right, and that's also why they have a port on this side for your SD cards. And I just want to check out the guts in this thing really quick, because it's what's inside that matters. I think there'll be screws under these feet here. And oh, that's nice, they have these little clips in the feet so you can put them back. Alright, there's the Wi-Fi antennas. This does support the Wi-Fi 7 protocol. Then we'll open this up. That's a 2TB SSD. And then there's the dual channel 32GB of DDR5 RAM. That's not bad at all. And then on the other side of this is the CPU. But unfortunately, as a software guy, I don't have the right screwdriver to get in here, but that's alright. We're about to get close up and personal with the CPU in a different way. Just plug in my USB drive to the front, along with a keyboard. Which button is it to get into the firmware? Okay, it wasn't escape. Gross, Windows 11. But as long as I'm here, might as well do a benchmark really quick to see what I'm working with. And that's not bad at all. This CPU is certainly nothing to sneeze at, and while the Geekom A9 Max isn't designed for intense gaming, it'll hold its own with anything you throw at it since it's an all-around fairly powerful workhorse, and that is something I'll be exploiting later on. So anyways, let's restart here. Let me try delete. Okay, there we go. So first I've got to turn off secure boot. Oh good, that's already off. Then I'll just set my USB to be the #1 boot priority. And let's restart. Alright, I feel the freedom coursing through my veins. Let's make a game. Starting with a timer. Of course, you gotta have a timer. I saw earlier in the runtime services tables there was a get time procedure, and this is fairly simple. It'll return an EFI time structure and an EFI time capability structure. So I'll call that, and then from the return time structure, just for testing purposes to make sure everything's okay, I can extract the current month, which is September at the moment, so I should see a 9, and that should be the digit 9, so to turn that into the Unicode character 9, I'll add 48 to that, and then print that with an M on the end. Compile, and I've made a batch script that will assemble and link everything and then even move this program onto the flash drive, so all I have to do is just unplug this and then put it in the Geekom A9 Max, power up, and there it is. It's September. Using this function, it shouldn't be too hard to create a simple 1 Hz time loop that will output the current second. I can take the output time structure and set aside the seconds value in another variable for comparison. Then, after calling the getTime function once more, I just need to compare the new seconds value with the old one. If they're the same, then go get the time again. Otherwise, it means that at least 1 second has passed, so I can print and save the current second and jump back into the loop. That seems to be updating at the right time interval anyways. Oh, there it goes back into numbers. Oh wait, there's 60 seconds in a minute, not just 10. Yeah, this is working just fine. Now, getting a sub-second timer to create a 60 Hz loop requires using the 4-byte nanosecond portion of the return time structure. So 1 billion divided by 60 is 16,666,667 nanoseconds per frame, or rounded down to 666 for all sixes. Luckily, this timescale I'm sure no one will notice being off by 1. So, subtracting the last frame's nanosecond value from the current value, if the result is less than 16.6 million, then 1 frame of time has not yet passed, so sit down and keep waiting. Otherwise, I can output the FPS count. 60 plus 48 is 108, in ASCII that's lowercase l, so it should say LFPS. And that is an L, but not the one I wanted. I even accounted for the carryover problem. What's going on here? This is good code, there shouldn't be any issues. I'll give a bit of a spoiler here, this is not the first time I've plugged this in. At this point, I'm just going to dump the contents of the nanosecond variable onto the console to see if I can figure out what's the issue. 0? Wait a minute. I read something about the time resolution before in the UEFI documentation. Where was that again? Oh, it was in EFI time capabilities. Alright, I already have that. It says if the resolution is 1, that the device only reports time to the resolution of 1 second. Okay, let's output this resolution to the console then. Please don't be 1, please don't be 1, please don't be 1. What can I do without a high frequency clock? Create a game running at literally 1 frame a second? Forget it. Wait a minute. Sisk, that's it. There's an instruction for everything. And while it isn't as easy as saying, computer, what time is it? There is a read timestamp counter instruction tied directly to the core clock's timestamp counter. This 64-bit counter ticks once every CPU clock cycle from the system startup onward, which will be about 2 billion times per second on the HX370 here. And even though the CPU's clock can boost up to 5 GHz, this system supports invariant TSC, so it'll always be a standard 2 billion ticks per second. Of course, to have the game run at the same speed on different processors, I'll have the program itself calculate the proper number of CPU cycles per frame. Just use the UEFI getTime function to wait for a new second to start, then call readTSC and save that as the start value. Once another second has passed after that, use readTSC again and subtract to get the number of CPU cycles per second, then divide by 60 to get the number of CPU cycles per frame. Then, when the logic for each frame is completed, I can just wait for the proper amount of CPU cycles to pass and move on to the next frame. And my being a programmer is definitely showing through here because I want to aim for 64 FPS instead of 60 because it's a much simpler number to divide by, and who made the Babylonians in charge of the time my game runs at? And actually, let's push it even further, 128 frames a second. We're cooking now, but here's the thing. This is just the program doing nothing. If I'm going to keep this frame rate, all the other logic needs to be executed within these 15.5 million CPU cycles. That may sound like a lot, but this loop here uses over 5 million cycles itself, so these things can add up quickly. But it's finally time for everyone's favorite thing to look at.
The graphics.
Whether it's your classic black and blue firmware screens or ones with speedometers or whatever, it's all done with the help of the graphics output protocol. This isn't found in the system table, I'll have to grab it through the boot service's locate protocol procedure by passing in the globally unique ID of the protocol. The graphics protocol itself only provides a couple of functions, but that's really all I need. The GOP's mode structure contains a value for the maximum number of video modes supported on the system, and then query mode will allow me to see what are the resolutions and pixel orders of those modes. There are quite a few modes to choose from, but the one that grabs my attention the most is the 1280 by 1024 mode, since I could increase a 256 by 256 arcade screen up 4 times and have it perfectly fit the screen. So I can use the set mode procedure to select 1280 by 1024 if available. If not, tough luck, the program will just default to the first video mode. 1280 by 1024 is actually the default video mode for this machine setup, so while setting the mode will usually clear the video buffer, in this case it just didn't do anything. All that's left to use is this last procedure, BLIT or block transfer, which provides direct access to the video buffer. There are 4 different ways to use this function, passed in through the BLIT operation parameter, but the 2 I'll make use of are the first and third, to either fill in a rect on the video buffer with a certain color. Remind you of anyone? And this is 24-bit color, by the way, though it's formatted BGR, not RGB in memory. Or, for the third option, copying a data buffer to the video buffer. I've chosen to fill in the whole screen here, but I could just as easily fill in an arbitrary rectangle of any size. Of course, I can't just copy-paste in a regular PNG or even a bitmap, those all have some extra data to them, but a quick conversion into raw BGR pixel data does the trick, and I can include that data in an include file directly into the assembly, since ML64 doesn't like raw binary files. Then it's as easy as loading the pointer to that data, setting the proper coordinates, and calling blit. And this leads me into the plan for the graphics engine behind the game. Now, I may be showing my bias as a developer of retro consoles, but I'm going to develop a kind of picture processing unit in the software that will render a tile-based map mixed with sprites into an output buffer. Convenient since I can just steal the actual Zaxxon tiles and sprites. So in total it'll be 2 background layers, each with their own tile map capable of X and Y offset, with the top layer treating the background color as transparent, and then a number of sprite objects which will be rendered in the middle of the 2 layers. As an initial test of this PPU, here is the machine rendering the first background layer. Here it's incredibly small because, as I said before, the game's output buffer is only 256 by 256, but since the current screen's resolution is 1280 by 1024, I should be able to cleanly scale it up by using the blit procedure on each of the 65,000 pixels to turn each individual pixel into a 4x4 square of that color. And there it is. That looks really awesome, but check out the FPS counter. That is not 128 frames per second anymore. Apparently the 65,000 blit calls are taking its toll. But I am only using the 1 CPU core right now. For a second I'll jump into Windows. Gross, I know, but hang on, it'll just be a second. Looking at this CPU in Task Manager, you can see all the work that each logical processor in the CPU is doing. Each of the logical processors, 2 per core in this machine, is basically like its own CPU, since decades ago they figured that if you can't make your CPU go even faster, may as well give you 24 of them to share resources and do things in parallel. That's how the computer can run Minecraft Bedrock Edition so smoothly, because even though it's the inferior version, it being multi-threaded proves that no program should ever be written in Java. As for my UEFI application, the program is being run on a single core, but it is possible to make use of all the other cores through the EFI MP Services Protocol Startup All APs procedure. AP as in application processor, or every core besides the bootstrap processor, which is running the current UEFI application. This function submits a procedure to all other available APs, and since they share the same memory space, they can all read, write, and process this program's data in parallel. Now, UEFI services and protocols are not allowed to be called by the APs, so instead of the same method of blitting each pixel, I'll have them upscale the small output buffer to a 1024 by 1024 buffer instead. Each processor can look at a list of unrendered lines, find one, and then turn the 256 pixel line into a 1024 pixel line by duplicating each pixel 4 times onto the final output buffer. Then copy that line onto the next 3 in sequence before moving on to the next unrendered line. Once all the lines have been rendered, each processor can return, and the BSP processor, which was blocked since the AP started working, can resume execution and blit the rendered 1024 by 1024 buffer onto the video buffer. That's more like it. With 24 cores in total on this machine, that's 23 other cores acting as graphics processors, so each core only has to parse 11 to 12 lines per frame. That's the power of parallelization and taking full advantage of the system. 128 buttery smooth frames, give or take. I can definitely feel the fan running now, so I guess it's a good thing that this whole case is basically one big heatsink. With that, it's time to implement the second graphics layer. I've done a bit of work in the background so that the first tile map can match the tile numbers of the game's actual background, and then the second tile map is rendered on top of the first, but with any zero tiles treated as transparent, so skip the render, and any pure black pixels skipped as well. For now, I'll add the game title on top, calling it Space Game for x64. Then on each side add 2 columns of window dressing to mirror the arcade game, which output a 224 by 256 display. I haven't turned the sides black yet since I want to see the whole screen while I'm testing, but I will once I finish it up. As for rendering sprites, I've also taken these directly from the arcade game's assets, then converted them into the proper image format and included them into the assembly file. The 64 sprites are rendered between the two layers, and since the sprites aren't tied to static tile maps, they can move around to any point on the screen, flying the ship around through user input. And about user input, I skipped mentioning it until now because I hate it. UEFI was not made with game design in mind. Weird, I know. It's mostly focused on console input and output. The current way input setup works is that when a key is pressed, it'll say this button is pressed and then set an expiration timer. If the program doesn't get another key down event in that time, it'll expire and turn the button off. This is the best I can do since UEFI only supports key press events and they're just regular key presses, like hold the key down and it'll send one event, wait a second and then start sending more events. So it's just absolutely garbage for game input. You can see as I move the ship around, because I have to make the first timer extra long, I'm just tapping the keys, but it keeps pressing the button for a ridiculous amount of time. It just isn't working. I'm going to need to rethink the input. If I was a smarter man or a dumber man, I would just go straight into the USB stack and just take what I need. But I'm just barely smart enough that I can tell that it looks like a mess and I don't want to go through that door. If this computer had a PS2 port, then I could read port 60 and 64 to handle keyboard input directly. I know, when's the last time you bought a computer without a PS2 port, but time marches on. After taking another look through the UEFI documentation, I think I've found one procedure that I can get instant feedback from, the simple pointer protocol's getState function. This procedure will return the x-axis and y-axis relative movement of the mouse in terms of some percentage of the horizontal height of the system, along with 2 Boolean button presses for the left and right mouse buttons. So I can turn the mouse input into a joystick thing, with the left click letting the joystick unlock and then the relevant movement in the x and y axis triggering movement. And then the right click can be the fire button, and that covers all 5 inputs used by the game. I've designed these 2 sprites on the bottom right of the screen to show the output, so let's see if it works. The joystick controls are so much better than the delayed keyboard controls. It's super responsive, very slick. Whoops, yep, the program will crash if the ship goes out of bounds, but that's to be expected. You think I put any memory controls on this? Of course, the ship shouldn't move around like that anyways. It should move around like this. That's smooth. 128 FPS smooth, and the altitude sensor at the left is like a butter even the Amish would be jealous of. And well, at this point, I'm at what I would call the J90 stage, as in the job is about 90% finished with everything new, but of course that means I'm only halfway done with the effort I need to put in to finish it up. So with everything from the scrolling backgrounds to the enemy spawning at certain locations to hitboxes and everything else, there's basically nothing novel here, it's just the same things with only a handful of interesting tricks. So without any further ado, let me show you what true freedom looks like. once again for letting me use the Geekom A9 Max for completely non-traditional purposes here today. Thank you, Geekom. Very cool. As you know, sponsorships are a part of how I make this channel work, but from here on out, I'm only going to promote things that I think are actually relevant to you specifically, which makes me personally feel more comfortable as well, and why I'm happy to partner with Geekom. Of course, we already saw the benchmark results for the A9 Max, so obviously this machine is no slouch. Even when it comes to hefty tasks like 4K video editing and processing, the experience for me has been very smooth and lag free. That's really helped by the 32 gigabytes of RAM that it dynamically shares with the Radeon graphics side of things. And I know what you're thinking, really integrated graphics, but honestly, the technology has come a long way in the last few years. It's nothing to sneeze at. Seriously, big kudos to the engineers behind the silicon for being able to push such high FPS in a number of popular games. I also did forget to mention that there are two more USB-A ports on the back, so that's six in total. So between all this I/O and the ability to upgrade your RAM and SSD, this really is a computer made for both creators and developers. And while this device is giving off some serious Mac Mini vibes, you can rest easy knowing that you're still safe in the land of x86. So whether you're a student looking to get your money's worth out of a computer, a creator who doesn't want to experience any more lag, or a developer who needs a more capable machine, you're going to want to head down to the link below and use the coupon code in the description for 6% off. And at $999, that discount goes quite far. As for Space Game for X64, you can check out the code on GitHub, but if this video just wasn't technical enough for you, I'm going to be doing a very thorough breakdown of this project on Patreon and through YouTube memberships, which will be out in a week or two from the time I'm publishing this video, so head over there and check that out.